This is a presentation on fuel cells for New Mexico State University Chemie 361. This is Group 1, Ceresa Medina,
Evan Saunders,
and Peter Trapka.
A fuel cell is a device that uses chemical energy to make electricity. Every fuel cell has a positively charged cathode, negatively charged anode, and electrically conducted electrolyte. Alkaline fuel cells, or AFCs, have an alkaline electrolyte. One strength is that it has inexpensive catalyst choices, and unfortunately a weakness is that it has a high reactivity to carbon dioxides. Alkaline fuel cells were used on the Apollo spacecraft and the orbital space shuttle. Direct methanol fuel cells, DMFCs, are powered by pure methanol. A few strengths are that they don't have the same fuel storage problems typical of some other fuel cell systems. They're easy to transport and supply to the public using our current infrastructure because it's in a liquid. Because of their size, DMFCs are often used for portable fuel cell applications, like for your cell phone or your computer. Solid acid fuel cells, or SAFCs, are solid acids that are chemical intermediates between normal salts and normal acids. They're a rugged and low-cost stack platform that operates easily on commercially available fuels. They're used for remote power for monitoring and automation in industry.
The PEMFC membrane is made of a proton-conducting polymer, most likely a fluoropolymer like PFSA. Applications are transportation, stationary, or possibly mobile applications. The advantages are low operating temperatures of maximum up to 100 degrees Celsius, cold start capability, and high power density. Challenges are the hydration of the membrane as well as byproduct management, which is water, as well as a low CO tolerance. The PAFC membrane is made of concentrated or pure phosphoric acid, which is retained by a silicon carbide layer. Applications are most likely stationary, like power generators for buildings and for large vehicles. Its advantages are high operating temperatures, which makes byproduct management much easier, and its higher CO tolerance than PEMFC, for example. Challenges are its low CO tolerance at lower temperatures, as well as the lower power density.
The last fuel cell is the solid oxide fuel cell, or SOFC. These use a solid ceramic electrolyte like yttria stabilized zirconia. They also work at high temperatures of 800 to 1000 degrees Celsius. Unlike other fuel cells, oxygen anions pass through the electrolyte, not the hydrogen cations. Applications, SOFCs are often used in power generation, ranging from about 5 kilowatts to 3 megawatts. One can also be used as an uninterruptible power supply in case of power outages. Cogeneration is another, in which an SOFC's waste heat can be used for water and air heating. Advantages include that they use a solid electrolyte, so they can have many different shapes. They can also run on many hydrogen-containing fuels like hydrocarbons and biogas. Also, the high working temperature removes the need for the expensive platinum catalyst used in other fuel cells. And with cogenerations, efficiencies can rise from about 60% to 85%. The challenge is the high temperature. It's necessary for the YSZ to have good ionic conductivity, but it also means that SOFCs have to be durable and well insulated. This limits them to mostly stationary applications. It also requires a long startup time, usually 10 or more minutes.
Fuel cells can be considered a clean energy source depending on the fuel type, but they are generally expensive, and the manufacturing process as well as the disposal is still hazardous.
Some final things to consider include what our society can accomplish by utilizing this fuel source on a large industrial scale.